Hi, this video covers some C++ code that implements the binary search tree insertion algorithm from the previous video. If you haven't watched that video yet, definitely watch it because this builds directly on that algorithm idea. We're really only going to present the code here. First, let's review the data types that we have for our binary search tree. We need one class for a node in the tree and a second class for the entire tree. This is the binary search tree node class. It's a template class with two template parameters, k for the key type and v for the value type. We are using our tree to implement the map abstract data type, so every entry into the tree is a key and value that are associated together. There are 4 data members in the class, 3 shared pointers to other nodes. There's the parent pointer, left pointer, and right pointer. And then there's also a standard pair of k comma v that's the contents of this node. The constructor initializes those 4 data members. The argument order, I'm trying to go top to bottom, left to right, the way we read English text. So the first argument is the parent pointer, kind of on the top row of the node, and then the bottom row of the node is the left pointer, the contents, which is a pair, and the right pointer. That's pretty much it for this class. There's also some accessors and mutators that I hid for space on the slide, but they're very straightforward, just setters and getters for those 4 data members. There's really not a lot else going on in the node class. Now let's look at the tree class, the binary search tree class that represents the entire tree. It only has 2 data members, a shared pointer to a node that is the root pointer, and an int size to keep track of how many pairs are in the tree, and that's all you need. The default constructor creates an empty tree. We initialize root to null. The idea is that the root pointer is null when the tree is empty, otherwise it points to the topmost node in the tree. Size is initialized 0 to begin with, and that's pretty much it. There's a whole bunch of other member functions. We're going to be covering those one at a time in these videos. Now let's look at the insert function. Remember that we factored the insert algorithm into some smaller pieces. So the insert function itself is not too long, but it calls into some other functions that do some of the work. Insert is given a pair to insert into the tree. It returns a Boolean to report whether we actually had any effect on the tree. So if the tree already contains the given pair's key, then we're not going to reinsert and overwrite. We're just going to say can't do anything in that case, and we return false. False means we did not change the tree in any way. We're using the contains function that we covered in a previous video. So contains is given a key. We've got a pair here, so we need to get the key out of the pair. It's the pair.first is the key of that pair. So we just call contains, and it returns true or false to tell us whether that key is present. If it is present, we return false. That stops the insert function, and we're done. If we get past the if, then we need to actually go in and put a node into the tree, and we call the insert node function and give it the pair. We have to do standard move because this is an R value reference. That's kind of a C++ technicality. We'll cover the insert node function next, but it does the work of finding the location where the new node should go and putting the node there and updating all the surrounding pointers. Then we increment the size just to keep that straight and return true so the caller can tell that we did in fact change the tree somehow. So now all that's left is this private helper function insert node. This is a private function because we don't want the external caller calling it. For one thing, if someone called insert node without updating the size, then the size would be out of sync. So this is a private function. It's only to be called by that public insert function. And this has one responsibility, which is to find where the new node should go, put the new node there, update pointers. That's all. It doesn't deal with updating size or returning true or false. That's the job of the insert function. So we've got the loop here that decides where the node should go. You'll have to excuse some unconventional white space formatting here. I did that so that this would all fit on one slide. We need 2 pointers in the loop. The child pointer is really where the action is. It starts at the root and works its way down to the bottom of the tree until that eventually becomes null when we go past the last leaf at the bottom down to a null pointer. But we need to remember the last node we saw in that process. So we have this other pointer called parent that keeps track of the last node we saw above the child so that when child becomes null, we remembered where the search ended. So here we've got a while loop, while child. That means while child is not null. Parent shifts down one level to the old child, and we have to decide how the child shifts down one level. And if pairs first, that's the key in the pair, is less than the child node's key, then child equals child left. That means shift down to the left, follow a left child pointer. Else, go down the right child pointer. Note that insert node assumes that the key is not in the tree. So I don't have a if pair.first is equal to key case. We know that we'll never find a node whose key is equal to this pair. That's a precondition on this function to work right and to be simpler. So when this while loop ends, child is null and parent points at the leaf node that ended the search. We reassign child to become a newly allocated shared pointer to a BST node. The parent of this node is whatever the search found to be the last node at the bottom of the tree during that search process, and this is a leaf node, so the left child pointer is null, the right child pointer is null, and we put the pair contents into that node. Again, we have to do std move to make our value semantics work. It's kind of a C++ reference technicality. The last step is to update an incoming pointer that points at the node so that the node is actually connected into the tree. And there's three cases. The first one is if parent is null, if not parent, then that means that there's no node above this new node we just created, child, so that means this is the new root node. So we just say root equals child. That's it. That's the tree's root data member. Otherwise, this node does have a parent. We have to decide whether to update the left or the right pointer. And we can do that by comparing the keys again. So if the pair's first element, meaning the key in the pair, is less than the parent's key, then parent's left gets set to become the child. Parent set left to become child. Otherwise, parent set its right pointer to become child. So that's it. That's the insert